Community Project Club. Today we're going to have Zach Nabavian talking about his project of forecasting energy demand in art. Okay, Zach, if you could take it away.
All right. Thanks, Lydia. So, yeah, for this project, for this meeting, I wanted to share this Quarto slide deck I made. All right, so you can see my screen. All right.
Yes.
So, so the goal of this project was to develop my skill set in using forecasting packages in R, mainly the Fable package. And I wanted to apply those statistical techniques to this data set of hourly energy demands from Spain. And I picked this data set because there was a lot of there was just a lot of data there, so it was very easy to pick out trends and seasonality. I feel like with smaller data sets, it's a lot harder to make forecasts that are precise. And also, as a part of this project, I made a series of LinkedIn posts documenting my progress on it. And I concluded by sharing a summary post just describing the whole thing. And I have links to each of these here. And after this presentation, I'll share this Quarto presentation on my GitHub too. So for some more context on the data set, it contains 4 years of hourly electricity demand data from Spain, covering the whole country. And it also contains weather data from the same period. And I've also linked to the datasets Kaggle page here. So I knew from the beginning that seasonality would be a big part of forecasting this project. But what's interesting about it is that there are actually multiple kinds of seasonality in the data set, and that was actually going to be a major problem for me because the kinds of forecasting models I was considering using, they only really used one kind of seasonality. So the data is seasonal by hour of day, by the hour of the week, and excuse me, by the day of the week and by the month of the year. And to show that I have, wait a second, I have these series of box plots here that I made, which shows the distribution of demands by each hour of the day. And I also have similar plots for day of the week and month of the year. But backtracking to the hour of the day box plot, you can see that it's going to be the largest, that the differentiation between each hour is going to be the largest. And so we can see that demand peaks by around midday and it troughs and it's at its lowest in the early hours of the day down here. So when people go to sleep. And for these other kinds of seasonality, the effect is much smaller. So for instance, by weekday, the demand is mostly the same for most of the week. It tends to be lower on weekends though. And month of the year, I see overall that the effect is the smallest here, but we do see some peaks in the summer months and also in the winter months. And I'll talk about that more later on, that demand seems to be higher during both hotter months and colder months. And so it's not necessarily a linear correlation. So as I said, finding a way to forecast this data set that in such a way that accounts for all 3 kinds of seasonality would be very challenging. And at the start, I had a few ideas for this. None of them were that great. One was just to build a model that just uses hourly seasonality. And I thought that might be good because hourly seasonality is clearly the strongest effects. Another idea I had was to try to incorporate all 3 by including Fourier terms in a regression model. Now, I did try this, but the issue is that even if that made the forecast more accurate, it took much longer for the model to run, and that became a very big problem when I tried to forecast for the whole whole data set as opposed to just a narrow range. And I really wanted this model, the models I used, to run quickly and be simple to explain. I did eventually find a better solution to this that I'll address later on, though. So, like I said, tackling the multiple seasonalities would be, I thought, the major challenge of this project. So at the start, I just wanted to experiment with some basic tools, and I kind of wanted to avoid the problem of multiple seasonalities. So I just focused on 2 months in 2015, January, and the first 2 weeks of February. And by doing that, I could kind of minimize the effects of seasonalities. If we're just looking at 2 winter months, I don't need to worry about seasonality by month. And okay, seasonality by week would still be a bit of an issue here, but again, just for getting started, I'm just going to focus on hourly seasonality. So what I have here is this table showing these accuracy measures for each of these kinds of models, starting with this naive model. What all this does is that it just assumes that the last value the forecast took, the last value the data in the data set took, that would just continue throughout the period that we'd be forecasting. So to clarify, for this smaller projects, I just use the first month of January, data from the first month of January to forecast, the first month of 2015, January, to forecast the first 2 weeks of February. So my training data was all of January, and I just wanted to forecast the first 2 weeks of February. And I wanted to use these different basic models to do so. And these naive models, the point is just that whatever the last value in your training set was, that's what we'll use as our forecast. And these seasonal forecasts, okay, the idea here is if we're taking a seasonal forecast by week, say, whatever's the last value in, say, Friday, we're going to just use that for all the Fridays. Mean is much simpler to explain, honestly. Just average all of the data in our training set and use that as your forecast. And I also have a naive forecast, but this time the season is by hour, and I found this was much more accurate than by weekday. That shouldn't be too surprising because our hourly seasonality was the strongest. But the strongest forecast, just using this in this smaller time frame, was this ARIMA model. And this was the strongest forecast across pretty much any accuracy measure we used. So at the beginning, so again, as I was getting started on this project, I focused on just this small portion of the data set, the first month of 2015, January, to forecast the next 2 weeks. And it seems like this basic ARIMA model was going to be my best bet. And I thought that this would be my baseline to build up a more complex model on. Now, when we try to forecast for longer timeframes, so for some context, after I moved on from this first period, I tried to forecast a much longer time frame, and I tried to build more complex models, and that came with several issues. So these are some issues with more complex models I tried to run beyond those I just talked about. These models are much harder to explain, and they take much longer to run. At one point, I tried to build a machine learning model, but I decided against that just because it was taking so long to run, especially on this very large data set. And whatever model I settled on, I wanted it to be simple and easy to explain. And these more complex models, they just weren't cutting it. They were either just not as accurate as what I'd done already, or they just took much longer to run, or both. We had both of those problems at the same time. So going on to the next phase of the project, I wanted to forecast on a much longer time frame. So the idea this time was to take the first 3 years of the data set and forecast the last year. And this time, accounting for all of those kinds of seasonality would be very important. It would be much more important than just that narrow time frame I focused on at the beginning. And some things I noticed that were all of those forecast models I was using for the short-term window, they were much less accurate here. And I wasn't too surprised by that because it's just much harder to forecast a much longer time frame. So at this point in the project, I did hit a wall. I wasn't really sure how to approach the rest of this project because like I was saying, any more complex models I was building were just taking longer to run or much less accurate. And so I wanted to see what other people were doing to forecast similar data sets. And I was very interested in just what people who actually work in this industry do. And so I found this academic journal article that discusses forecasting techniques for electricity demands. And I'll discuss the model it suggests later. And it's interesting in that it's very different from any of the other models I had been using. The other models I've been using were all simple time series models that take previous values of demand and try to extrapolate from those. But what this one does is that it's not a time series model at all. Instead, it's at its baseline a regression model on temperature. And yeah, looking at this slide, I realized that the formatting for the citation got messed up here. Yeah, I'm going to need to fix that later on in the Quarto doc. So this is the regression model that the academic journal article suggests, and it looks complicated, but I don't think it's super complicated once we dive into the weeds. This is a regression model on temperature. So it tries to run a regression model on the temperature values at that point in the data set. And what's interesting about this is that this isn't a normal regression model. It's actually a cubic regression, and that's what this t cubed plus t squared plus t, that's what this is showing. And I'll get to why they use a cubic regression in a moment. But this model, it also uses interaction term. It also incorporates classification terms for hour of the day, month of the year, and by weekday. And so this was also a good model for incorporating all three kinds of seasonality, and it does so in a way that doesn't take super long to run. Now, I wanted to talk about why they use a cubic regression for this, and I think the easiest way to show that is to show this scatter plot here by plotting temperature with actual demands. And it's interesting in that there is a relationship here, but it's not strictly linear. You see that it kind of dips in the middle here. And I talked about this before in that electricity demand, it is related to temperature, but not in a linear fashion. It peaks in colder temperatures and also in hotter temperatures, and a cubic regression was just a good way to account for that. It just going with a strict linear model wasn't the way to go here. Now, at the same time, this doesn't follow a cubic regression exactly, and so I also needed those classification terms for those seasonality terms. Now, what this table is here, it's much like the table I was showing at the start, but this time it is for covering that longer time frame using the first 3 years to forecast the last year. And that regression model I was talking about, it was by far the most accurate, again, by any of these accuracy measures I was talking about. Now, I did try to include one more addition to the regression model, just and that's to include this recency effect here. And so what that does is that includes an additional term for a moving average of temperatures from the previous month. Now, I thought this would make the forecast more accurate. In fact, the journal article was discussing about how these recency terms could make the forecast more accurate. In this case, though, there just wasn't a huge improvement over the baseline regression model. And so I still think there are ways that we could improve the accuracy of these models. And even though I did end this project after this point, I am interested in trying to find more ways to make this more accurate. But this is where I decided to settle on the projects, and I wanted to end it here because I thought I had learned some good lessons from this experience. And before I get to those, I did want to talk about some practical issues with this regression model. One is that it incorporates real-time temperatures that correspond to the hour of the day we're trying to forecast. And there's an issue with that in that we can we can train a model on historical temperatures, but what we can't do is we can't really use future temperatures in our regression model. And what I mean by that is, let's say we're trying to forecast midnight tonight. We don't know for sure what the exact temperature is going to be at that point. So I can't just feed that temperature into the regression model. And so I think if we want to actually take this model and implement it in the real world for an energy company, I think you'd need to combine that with a corresponding weather forecast model. And there's going to be a lot of uncertainty in that. And so I think this regression model will be even less accurate than what my table earlier showed. So now some additional notes on this is that I don't think this model is the most accurate thing in the world. It's not really meant to be. And I'm sure there are better, more accurate ways to forecast this data set. And the point was really for me to learn about this specific data set and this kind of data and to see what kind of forecasting I can do in R. It's not meant to be some huge revolutionary thing that's going to upend the industry or anything like that. And once again, I kind of screwed up the citations here, but getting back to those lessons learned, I think the main lesson is that in trying to forecast these kinds of data, domain expertise is critical. In that I found personally that it's better to really learn what other people are doing to forecast this data and what's accepted as domain expertise. It's better to do those things than to try to build an endlessly complex model. And that's what we saw in the data earlier. The more complex models weren't really working. These generic time series models weren't really working, and what really did work was this regression model that experts had already built. And as I said at the beginning, I also presented this project in a series of LinkedIn posts. And so that was a great learning experience for presenting this project and seeing how an online audience would react to it. And so that's my presentation. I wanted to cite some sources here. One was the book I used to learn how to write all these forecasts in R. And the other was the academic journal article I was talking about where I got the idea for this regression model. And that's my presentation.
Thank you.
Thanks so much.
Yeah, it was great presenting this here. So I do plan on uploading a fixed version of that Quarto doc. In the meantime, do you have any questions for me?
Yeah, I'm curious. So, what's next for you as far as projects now that you've wrapped this one up?
So So I did wrap up this project, but like after like summarize like writing these summaries and this quarter talk, I kind of want to continue with it and see if I can improve on it some more. And someone gave me an idea to make a Shiny app out of it, and
Oh,
I'd be interested in writing a Shiny app that shows graphically how different forecasts perform.
yeah. Okay, that sounds cool. Yeah. And, I think that's it for me as far as questions. Anyone else? Federica, Tinashe? Yeah. Let's see.
So Tinashe, let's see. So he posted a question in the chat. So, but he asked, could you tell us a bit about how you decided on the ARIMA model and how popular that is in the field? So I settled on the ARIMA model for a few reasons. So I was trying a bunch of different forecast models that this book recommended, and the ARIMA model was seems like at the time it was the best for a few reasons. One was that it seems like the most accurate method that I had at that moment, and another reason I liked it was because, and I didn't really get into this during the presentation, but it did the best job of minimizing autocorrelation in the residuals. What that means is that if we have an error at say 12 o'clock midnight, we don't want that residual to be well correlated with the residuals for the following or the previous hours. If that's happening, then that's a sign that there are ways you can improve your data set. And the ARIMA model seems like it did the best job of minimizing that autocorrelation. Now, I don't believe this ARIMA model is all that popular within this specific fields. From what I read in that journal article, they're much more interested in using these regression models on temperature, and they're very much not interested in using a traditional time series model. Yeah, I hope that answered your question. Um, so
Yeah.
so I think we could wrap things up here.
All right, great. Well, thank you so much, Zach, for presenting your project today. Really enjoyed it. So for next month, our next meeting will be, what is the date? Okay, April 12th. We don't have anyone signed up, so if anyone in the meeting or anyone watching on YouTube, if you want to sign up and join, you could check it out and join the community at DSLC.io. Thank you all for joining today, and I hope you all have a great rest of your day. Bye.
Yeah, take care. Yeah, thanks for listening to me.
Okay. All right. I'll see you all. Bye.
See you.